This lesson deals with a wideband common-emitter amplifier analysis. You can find these notes in the ECE302 ebook in Chapter 10, starting on page 21. Let's take the circuit that we had in Chapter 5 on page 4, which was a common-emitter amplifier. And I took the resistor that was here, which I had said was 500 ohms, and I put 50 ohms here. I purposely picked it to be that large so that I would get a voltage division before I amplified it. But with the input impedance of this amplifier, you want to make this much smaller. I went back to 50 ohms, which would be what you'd have in a function generator. The file is the same as we had in Chapter 5, except I'm going to put in the model from the PSpice library for the 2N3904 transistor. I'm also going to plot the frequency response from 1 Hz to 1 GHz. That's 9 decades. And if you do 22 points per decade, you have about 198 points. I'm also going to ask for the operating point so we can see what the DC operating point is, but also the AC parameters. And we can compare those with our equations that we derived over the last several pages. What's shown here is part of the output file, where I have the DC operating point numbers, and then I have the AC model parameters. I also showed this printout of the .model command. In our input file, there were quite a few terms per line. Here it's printed out one line at a time. And had you typed that file, you could check whether you made a typing mistake or perhaps maybe omitted a term. Page 20, we had collected our formulas for calculating the AC model parameters. So let's see how those compare to SPICE. In most cases, SPICE is calculating a true slope. So we're going to be using our formulas as an approximation to that. So we'll get similar numbers, but probably not exactly the same. I said that GM was approximately I sub CQ over 8F V sub T. And I sub CQ up here is 4.19 milliamps. A to F is listed over here as 1. And V sub T is 25.865 millivolts at room temperature. That gives me 162 millimos, and you can see over here GM is 153 millimos. R sub X in the model is the value of R sub B, which was just specified up here as 10 ohms. Our pi was approximately 8F V sub T over I sub BQ, and I sub BQ here is 25.3 microamps. And you get 1.02K. It was calculated here as 1.17K. R sub C here is listed as 1 ohm, and that's our R sub C in the model. And then R out can be found by the operating point information and the early voltage, and then also the operating current. So the collector emitter voltage up here is 6.6 volts. VAF is 74.03, and I sub C we found before is 4.19 milliamps, and that's 19.24K. And here was calculated as 19.1K. The value of the base emitter capacitor, which we also call C pi, was this formula listed earlier in the chapter and recapped on page 20. Put the numbers in for this. Tau sub F is listed here as TF is 301.2 pico. We found GM to be 153 milli back up over here. I'm going to use the values here to see if we get a number close to the calculation by SPICE versus what we hand calculated over here. And CJE0 is CJE, which is 4.493 pico, and divided by 0.5, and then 1 plus ME. ME is MJE, which is 0.2593, so add 1 to that. Then 1 minus a half times that same number, and then MJE again, and then the base emitter at the Q point is up here. It's 0.702, and then our value of V0 is defaulted to 0.75. So this first term I get 46.08 picofarads. From this next term I get 10.75 picofarads times 0.6. That gives me 52.67 picofarads, but about 86% of this number is this number right here. This is what we had approximated initially for the value of C pi. Then we have the base collector capacitance we called C mu. That's C sub JC0 over 1 minus V sub BCQ over V sub C0. Look up on top here. C sub JC0 is C sub JC, and that's 3.638 pico. And then the base collector voltage is also listed up here as a minus 5.9. That minus with this minus cancels, then we get a plus. And then MC is the term MJC, which is 0.3085. Gives me a capacitance between the base and the collector of 1.856 picofarads. F of T is called the gain bandwidth product, and this is where the magnitude of the AC beta crosses 1. Frequencies above that, the transistor amplifier can't amplify. So it's an interesting number to calculate to tell you what frequency you could use your amplifier up to. That was 1 over 2 pi GM over C pi plus C mu. GM was 0.153 from the calculation that SPICE did. And then we had the capacitance that SPICE calculated 52.8 picofarads and 1.86 picofarads. Calculated 445.5 megahertz, and they're calculating 447 megahertz. Formulas are close. It won't be exact, but we're going to use SPICE to find these parameters. And we're going to use this to do our calculations for predicting bandwidth. Plotted in this first graph the ratio of V7 to V2, and V7 is the voltage across the resistor R sub L, which was node 7, and the input voltage was defined at node 2. So taking that in dB, I get a Bode plot like the shape that we were looking at in ECE302. We have what's called a mid-band gain, which is 39.825 dB. We're going to hand calculate this and compare it. 40 dB is a gain of 100, so we're in the ballpark of what we had calculated previously. The 3 dB point here is at 14.2 hertz, and the corresponding 3 dB point here is 47.8 megahertz. This is the frequency where the voltage gain drops by 1 over the square root of 2, and when you square that, you get half. So when you're finding power, these are called the half power frequencies. I also plotted the phase angle, and this is taking the phase angle of the numerator minus the phase angle of the denominator. In the pull-down menus, there is no P, so you have to actually type this. So here's a plot of angle versus frequency. And you can see in the mid-band that we have a phase shift of minus 180. Our gain is negative at these frequencies. Now that we've seen the magnitude of the voltage gain and the angle versus frequency, can we hand calculate those results and predict the mid-band gain and the 3 dB frequencies? Let's go back to our schematic on page 21, and let's put an AC model in for every component. We're going to replace the transistor and put in the Giacoletto model. And we had a battery hooked up to the 10K resistors, shorting that to ground. We also had a 1K resistor hooked up to the battery, short that to ground. And the rest of it is putting in the circuit that's on page 21. In this particular model of the transistor, there was a value for R sub B and R sub C, but there was no value given for R sub E. Typically, they'll put this value here or here, kind of lump the total resistance together. But this resistor is much higher than this one. Now this will cause an effect that we'll see in the next video. We're going to analyze this circuit. It's a pretty big schematic. If you did a source transformation here, that would be 1, 2, 3, 4, 5, 6 nodes, 7 nodes. This would be a 7 by 7 matrix. It would be very hard to symbolically solve this or even numerically solve it. Well, let's look at a couple of approximation techniques. We've been using some of these already. And the first one is to take a look at what's called mid-band analysis. And in doing that, we were shorting the big capacitors. We're assuming the frequency was high enough that these looked like short circuits. Inadvertently, we didn't know about C-pi and C-mu, so we were just treating them as open circuits. For mid-band analysis, that's what you need to do. Take the big capacitors that are in microfarads and short them, and take the small capacitors and open circuit them. I'm going to neglect this 1 ohm resistor here because it's just a voltage divider with what's here. But if I analyze this circuit and I don't get close to the answers I simulate, I go back and I put that resistor back in. Right now, if I short this capacitor, the emitter is going to be grounded. Short this, I'll have these two in parallel, and short this, I'll have this feeding this parallel combination. The equivalent circuit is actually quite simple at mid-band frequencies, and of course it's something we did back in chapter 5. These three resistors in parallel are about 644.2 ohms. What's new here is we've got a value of R0 now added in. And of course this is much bigger than this, so it won't have much of an effect. The output voltage is going to be equal to the current that flows into this parallel combination. It'll be a minus 0.153 V pi times 644.2. What's the voltage V pi? Well, here's our voltage V in across these elements. Here I've got two elements in series, so this forms a voltage divider with V in. The resistance here is 1.17K plus 10 added to 1.17K times the voltage V in is the voltage across V pi. So the resistor here didn't have much of an effect. We're getting about 99% of the voltage from V in applied to V pi. We can plug in this into the previous equation. Gain is minus 97.73. You take 20 log of the magnitude of that, you get 39.8 dB, and that's exactly what we had in our SPICE simulation. On page 24, we had a schematic for our amplifier by putting an AC model in for each component, and we'd put the Giacoletto model in for the BJT. The capacitors between the base in the emitter and the base in the collector are in picofarads or even as big as nanofarads. When you go in the lower end of the audio band, around 20 hertz or so, those look like open circuits because they're such small capacitances. For example, a 10 picofarad capacitor at 20 hertz has a magnitude of the impedance of 796 megohms. So if we were to throw those away, we have a model for our amplifier at low frequencies. Problem is, this is still pretty complicated. If you do a source transformation here, you have 1, 2, 3, 4, 5, 6 nodes. That's a pretty big matrix to try to analyze either symbolically or numerically. But there is a way to approximate the 3 dB corner by using another idea called the short circuit time constant method. The proof of this is done in the supplemental problem sets, and the proof is very different from how we use it. Let me tell you how to use the algorithm. It's like Thevenin's theorem. There's a technique, there's also a proof associated with it. Let's go through the method. To approximate the 3 dB frequency, we'll call it f of L of a transfer function. We're going to call it V out over V in. We'll set V in equal to 0. If this was V sub s, we would set V sub s equal to 0. You can solve for some output over input. Whatever input you're solving for, we're going to set it equal to 0. And for each large capacitor in our circuit, these would be things in the microfarad range, we're going to find their input resistance looking into those terminals with all the remaining capacitors short-circuited. And the reason why this is true is in the supplemental problem sets. If you do that for all n capacitors, the low-frequency corner is 2 pi times f of L, and it's the summation of the reciprocal of those time constants. We call them short-circuit time constants. We're finding the resistance looking at a set of terminals with all the other capacitors short-circuited. I'll call this tau sub short circuit I, where I goes from 1 to n. Let's take our amplifier that's on page 25 and let's short V in. There was a V sub s and an R sub s over here, but this short circuit disconnects that from the rest of the circuit. Here's my circuit that's left over, and I kind of exaggerated the capacitors to look like the terms that were done in the proof in the supplemental problem sets. We have 3 capacitors, and we're going to find the resistance looking into these terminals with the other capacitors short-circuited. That's the method of doing this. Let's start with the first capacitor here, C1, and I'll call that my tau sub short circuit 1. So I'm going to short circuit C sub E and C2. When you short this capacitor, this all becomes ground. Finding the resistance here is applying a voltage and measuring a current. And if you apply a voltage, there'll be a voltage induced here, but that's only put over to this side of the circuit. The controlled source has no effect on this part of the circuit. Looking in here, all I see is 10K in parallel with 5K in parallel with this series combination back to ground of 1.18K. Gives me a resistance of 871.5. If you multiply that by the capacitor that was here, which is 47 microfarads, you get 40.96 milliseconds, and the reciprocal of that is radians per second, 24.41. That's our first reciprocal time constant. We're going to find 2 more of these and add them together. Next, let's find the resistance looking into C2, but with the other capacitor short circuit. Here's C1 being shorted and C sub E. With C sub E being shorted, that makes this ground. If I were to apply a test voltage here and measure a test current, none of that voltage could get over here because there's no physical connection. The controlled source only works in this direction, doesn't work backwards. With no source hooked up here, we can't give any current or any power, so everything's equal to 0. That means that this controlled source is also 0, and looking in here, we then just see these 2 in parallel, 19.1K in parallel with 1K, and that's in series with 2K. And that's the calculation over here. Multiply that by the 22 microfarads for C2, we get 64.9 milliseconds, and the reciprocal of that is 15.41 radians per second. And lastly, let's find the resistance looking in the capacitor CE. And we'll short C2 and we'll short C1 and look back into here. Now if you apply a voltage, it's going to cause some voltage over here and cause this current source to do something. We have to leave this controlled source in. Let me do the following. Let me take this part of the circuit over here and see if I can simplify it. These 2 resistors in parallel with the short circuit is a little smaller than 1K or 667. I'm going to take this part out and try to get rid of this resistor by using source transformations. Here I've got these 2 in parallel, so I'm going to do a source transformation, convert this into a voltage source with a plus sign where the arrow head is, and then add a series resistor to the 667. If you take this times this, you get 2.922K times V pi. You can combine these 2 resistors together and get 19.767K, and then convert that into a current source by taking this voltage and dividing by this total resistance. That gives me 0.148 times V pi. This is an equivalent circuit to this. And I can do that because I'm looking for the resistance into these terminals. Let's put this into our schematic and let's continue on with the analysis. If we're looking for the resistance in here, we've replaced that part of the circuit with this equivalent. Between these 2 terminals, I have a 1K resistor and a 19.76K resistor because here's one terminal and here's ground. So what I'm looking for is something in parallel with these 2, and if I take these 2 out, I have a much simpler circuit to analyze. You could leave them in if you wanted to and apply a test voltage here and measure a test current, but let's even make the work a little bit simpler. Let me remove these 2 and then try to find the resistance looking in with those removed, and we'll put them back together with the parallel combinations. And we're looking into an emitter, and so that should look like a pretty low resistance. We'll apply a test voltage, measure a test current. The current coming in here is equal to this current plus this current. That's minus 0.148 V pi. And then the current in this direction is V pi divided by 1.17 K with a minus sign. What's the value of V pi? Well, it's going to be a voltage divider with this voltage. Whatever voltage is here, you're going to get 1.17 K over that plus 10, but this voltage is the negative of V test. Let's substitute this back in over here and here. We've got 0.148 and 1 over 1.17 K, both with minus signs, but I have a minus sign here, so that cancels them. And that gets multiplied by this ratio, which is 1.17K over 1.18K times V-test. All of this turns out to be 0.1476. If I take V-test divided by I-test and take the reciprocal of this, I get the resistance looking back, and it's 6.775 ohms. A very low resistance, and again expected because we're looking back into an emitter. We can now calculate the resistance looking into the capacitor CE. It's 1K in parallel with 19.767K, in parallel with the 6.775 ohms that we just found, and that's about the same value at 6.727. That set of terminals had a 2,200 microfarad capacitor, so the product of these two is 14.8 milliseconds, and the reciprocal is 67.57 radians per second. Our low-frequency corner can be approximated using this technique as the sum of those three reciprocal time constants. If we add those three up, we get 107.4 radians per second. If you divide that by 2 pi, you get 17.1 hertz. We measure with SPICE 14.2 hertz. And this is an approximation technique that will get us close to the value. But now we can see what's controlling the corner frequency. Obviously, we had a very big capacitor here, and that was needed because we had a very low resistance. And to get a number of similar size to these two, we would have to have a large multiplier times that small resistance. We'll talk some more about this in some of the supplemental problems. And this is a partial analysis of a wideband common emitter amplifier.